Welcome. In today's video, we're going to derive the mean and variance of the discrete uniform distribution. To begin with, let us define the PMF, or the probability mass function. So suppose that x has a discrete uniform distribution going from the interval a to b. Then the PMF of x, or the probability mass function of x, is given by the following. It is Px of x is equal to 1 over b minus a plus 1 for the values that x is an element of a plus 1, a plus 2, ... all the way to the final value of b. So, to derive the expectation of this random variable, well, we know it's a discrete random variable, so we're going to use the discrete definition of expectation, which is the sum of x across the support of x multiplied by the probability mass function of x. Substituting in our values, we know that x goes from a to b, so our terminals of our summation function go from x is equal to a to b. Then it becomes x times 1 over b minus a plus 1. Now, the first thing to note is that the probability mass function here doesn't actually depend on x. Because it doesn't depend on x, in other words, it doesn't depend on the terminal of the summation, we can pull this outside the front of the summation. So we can write 1 on b minus a plus 1, and we're going to still sum from x equals a to b of x. The next thing that I'm going to do is I'm going to make use of the knowledge that I've accrued over time, or that we've accrued over time, and I'm going to use a special known formula. This is simply the sum of integers, right? You can think of a to b as integers. But I'm going to know, I'm going to use the rule that if I start at 1, say for example, and I go to n, in other words, the sum of the first n integers, I know that the formula is 1 onto n plus 1. Now, if you're not familiar with this expression here at all, that's fine. There is another video available online on the channel, which goes through a proof using mathematical induction of this fact. Now, this applies, of course, for x equals 1 to n. We're starting the terminal at x equals a, and that's not a matter. That doesn't matter necessarily, because we can rewrite this summation as the difference of two summations, and I'll show you that in a sec. We can say this is the same as going from x equals 1 to b of x, and then we're going to subtract everything that comes before, so from x equals 1 to a minus 1 of x. In other words, what we're saying is we're going from a to b. That's the same as taking the full range from 1 to b, and then subtracting the range from 1 to 1 less than a. And so we're going to use that. And now, because of that, this is in the form that I've just shown you here, where it's x equals 1 to n. We can derive two formulas for this. So this becomes b minus a plus 1 this expression, the first expression here is simply b times b plus 1 over 2 minus the expression for a. It becomes a minus 1, a minus minus 1 plus 1 all over 2. Then from this expression onwards, we can actually take the common factor of a half outside the brackets. So that gives us 1 over 2b minus a plus 1. We put that here. That leaves us in this expression here with b plus 1, b plus 1, minus a minus 1, and then we can also simplify the last part of this bracket. A minus 1 plus 1 is just simply a. We can do a bit of expansion here. That can be written as 1 over 2b minus a plus 1. Close the bracket. Here we've got b squared plus b if we expand the first bracket, and minus a squared plus a if we expand the second bracket, part of that expression. Again, we've still got the 1 over 2b minus a plus 1. And now what we're going to use is we're going to notice that there are two squares here. And so we're going to use the difference of perfect squares, and that is of course b minus a, b plus a. That takes care of the following term, that takes care of the minus a and the plus b squared. We still of course have the b and the plus a at the end, so we've still got b plus a here at the end. And now you'll notice that there's a b plus a here and a b plus a here. We can take that out as a common factor, so let's do that in the next step. 1 on 2 minus a plus 1. Close that. So that would become b minus a plus 1 as the common factor, b plus a. And the common factor here's the 1 times your b plus a, which gives you that yellow part there. And finally, in this expression here, what we notice is that the b minus a plus 1 can actually cancel with the b minus a plus 1 in the numerator. Or, I say numerator, but it's not really technically here. It's outside the fraction itself, but it still can cancel. And then this finally simplifies down to, we've simply just got a plus b and a half applied, so we can write that as a plus b on 2. So there is our formula for the expectation of a discrete random variable. Next, let's take a look at the variance. So for the variance, we're going to first have to derive an expectation of the second moment, or expected value of x squared, before we can calculate the variance. So let's do that. The expected value of x squared. So by definition, again, it's x in the support of x squared this time, times the probability mass function of x. Again, we're going to go from the terminals of x equals a to b. We've still got our x squared, and we've still got our b minus a plus 1. Once again, the 1 over b minus a, the probability mass function, is independent of the index of the summation, and so we can take it outside the summation sign, so it becomes 1 over b minus a plus 1 over x equals a to b of x squared. And similar to before, what I'm going to use is perhaps another known fact, in that if the summation of x equals 1 to n of x squared, or in other words, the sum of the first n squares, right? The sum of the first n squares ends up giving us the following expression. It gives us 1 on 6 n plus 1, 2n plus 1. Now again, this formula here, I'm not going to prove it for us in this particular instance, but there is another separate video, again, mathematical induction video on proofs of equality, which goes through this in quite some detail of how we get there. So using this fact, let's continue for now. And again, in a similar fashion to before, where we had we took the terminal going up here, how we subtracted, or we expressed the summation from a to b as the difference of two summations. We're going to do the same thing here. So we can do this as, we can say that is the sum of x equals 1 to b of x squared minus, again, x equals 1 to a minus 1 of x squared. Now we can apply the formula that I have in yellow here. We've got 1 over b minus a plus 1 of 1 on 6 b plus 1, 2b plus 1, minus 1 on 6 a minus 1 plus 1, 2a minus 1 plus 1. Close the bracket at the end. So it's a bit of a convoluted expression here, but let's try and simplify as we can. The first point of simplification is, of course, to note the 1 on 6 and the 1 on 6 here can sort of come out the front as a common factor. So let's do that now. So we can write this as 6b minus a plus 1 out here as the common factor. I'm just going to leave the first expression as is for now, no need to expand, because the second expression we're going to just write as minus a minus 1 still. The a minus 1 plus 1 simplifies down to a. The 2a minus, or 2 times a minus 1 plus 1, we can simplify that down to 2a minus 1. And that closes the brackets there. And then finally, let's start our expansion here. 1 on 6b minus a plus 1. Close that, or put that the line there. Let's expand the brackets. So if we expand this term here, you'll get b times 2b. That'll give us 2b cubed. We've got a b times 1. That'll give us, b times 1 gives us plus b squared. Then we've got to go b times 1 times 2b gives us plus 2b squared plus 2b squared, and then finally you've got the b, the 1, and the 1 multiplied by each other, which gives you plus b. Now if we do the second summation here, the second product, we have a times 2a, which gives us 2a cubed. We've got a times negative 1, which gives us negative a squared. Then we will have negative 1 times a times 2a. So negative 2a squared again. And then finally got negative 1 times a times negative 1, which gives us just positive a. And we'll close that off. Well, this is still looking like a very convoluted expression. And quite frankly, there's a lot that we could do here. And moving on from here is going to be challenging, because it's not very clear how we can factorize this. And quite frankly, one of the things here is, ideally what I want to be able to do is I want to be able to pull out a nice factor of b minus a plus 1 out of this expression here. That's what I'm hoping for. So there's one thing that's standing out to me, and really it's sort of a luck of how we try and express this, but the one thing that's standing out here is that we have a difference of perfect cubes. Maybe remember, if you have a difference of perfect cubes, you'll be able to factor out a b minus a. So maybe somewhere down the line we're going to be able to get there. And I promise you we will, but I'm sort of trying to give you my thinking before in how we can sort of get to a factorization here. Sort of a pray that we're going to get there in some sense. So firstly, I'm just going to group those terms. 2b cubed minus a cubed together. Just those two terms. Now, whatever's left over is b squared plus 2b squared. So that's just plus 3b squared. And we've got a plus b. So we've got a plus b. Then we have a minus a squared minus 2a squared. So the minus will cancel out with that. So we'll have plus 3a squared. And finally, we've got a minus a at the back there. So not looking too bad. It's looking a little bit simpler, but certainly nothing that is really all that helpful. Now, let's try and do this. Let's try and expand or factorize this. So that'll give us 2b minus a, b squared plus 2a, plus ab plus a squared. That is, of course, the formula for the difference of perfect cubes. You've got 3b squared plus b plus 3a squared minus a. All right, so far so good. Let's do another line of simplification. 6b minus a plus 1. Now, again, remember, I wanted to get a factor of b minus a plus 1. I don't really want the 2 out there, because I could have the 2, but I just want to pull out the b minus a plus 1. So all I'm just going to do is I'm going to put the 2 inside the expression here. So b minus a 2b squared plus 2ab plus 2a squared. Again, we've got a 3b squared plus b plus 3a squared minus a. And you might be thinking, wow, we are not really getting anywhere. This is looking more and more complicated as he goes on. And you could be right, but I'm going to do something a little not counterintuitive, but a little bit sneaky here, where I want a b minus a plus 1, right? So what I'm going to do is I'm just going to write it in here in this expression, 2b squared plus 2ab plus 2a squared. But now note, I've added one lot of this particular expression. So now I need to subtract it away. 2b squared plus 2ab plus b squared. And of course, I've still got the plus 3b squared plus b plus 3a squared minus a at the end. And maybe I might get somewhere here because, let's go here, 6b minus a plus 1. Let's put that down there. We've got our b minus a plus 1, our 2b squared plus 2ab plus 2a squared here. Now, notice here our minus 2b squared will sort of cancel out components of the 3b squared. That leaves us with plus b squared. We've got our minus 2ab. Well, that hasn't really changed. There's nothing to collect like terms there. Then we have our, and I think I've made a slight error above. I wrote this as a b squared when I should have written this as an a squared, 2a squared in fact. And so now I have a minus 2a squared plus 3a squared. That gives me plus a squared. And then all I have left over here is the b minus a. And so we've got a plus b minus a. And again, we're going to have the 1 on 6b minus a plus 1. All over here, b minus a plus 1, 2b squared plus 2ab plus 2a squared. I think we're going to get somewhere because look, we've got a b minus 2ab plus a squared. That looks like a perfect square. In fact, it is. It's a b minus a all squared. And then we've got a b minus a here at the back, which I have accidentally moved to an awkward position. But now I've put it back, so we've still got our plus b minus a here at the back. I'm going to just be clever here and take a copy. And notice that what we can do here at the very end is we can take b minus a out as a common factor, which leaves us as b minus a plus 1. And would you look at that, we have a b minus a plus 1, we have a b minus a plus 1. We have got somewhere because that means we've got a 6b minus a plus 1. We can take a common factor of b minus a plus 1 out, leaving us with 2b squared plus 2ab plus 2a squared. And of course now we have the b minus a plus b minus a. Close the bracket. And of course don't forget the fraction here. And finally, after all that hard work, the b minus a plus 1 will cancel with the b minus a plus 1 here, and we're left with the following expression. 2b squared plus 2ab plus 2a squared plus b minus a all over 6. And that was a lot of work just to derive the second moment of the distribution. We haven't even got to the variance yet. So, let's finally calculate the variance of x. And we know by the definition of the variance, we can calculate it as the expected value of x squared minus the expected value of x all squared. We just derived an expression for the expected value of x squared. We can just bring it down the front here. We also derived an expression for the expected value of x. That was a plus b on 2, but we have to square it. This becomes, again, we can just take our value here, copy that down, no need to rewrite it just yet. We will expand this term here. That gives us a squared plus 2ab plus b squared all over 4. Now, what we need to do is find the lowest common multiple of 6 and 4, so we can express these on the same denominator. That just happens to be 12. So here the same denominator will be 12 minus something on 12. Now, to get this expression, so to go from 6 to 12, you need to multiply by 2. So you need to multiply the whole numerator by 2 to give you the same expression. That gives you 4b squared plus 4ab plus 4a squared plus 2b minus 2a. Now, on the second fraction, to get from 4 to 12, you need to multiply by 3. So we need to multiply by everything at the top by 3 plus 6ab plus 3b squared to give you the same fraction. Or the same fraction. And now we can actually cancel a bit out. We've got 4b squared minus 3b squared. That gives you just b squared. We actually have 4ab minus 6ab, so that gives us minus 2ab, and we have 4a squared minus 3a squared, which gives us simply plus a squared, and then we also have the final plus 2b minus a left over, and I've just factorized the 2 out there, over 12, which is equal to, I'm going to factorize this expression out the front. That gives me b minus a all squared plus 2b minus a over 12, which is equal to, in this particular instance, we can factorize the b minus a out, which gives us b minus a, plus 2 all over 12. Now, sometimes you'll see the expression written like this. In some instances, I'm going to do a little bit of a modification to this expression. You can actually rewrite this as b minus a plus 1 minus 1, and you might be thinking, why is he doing that? But the second expression you can write as b minus a plus 1 over 12. And then what you will notice is this is the formula for the difference of perfect squares. So b minus a plus 1 minus 1, b minus a plus 1 plus 1, and so this can actually also be written as b minus a plus 1 all squared minus 1 squared, which is just simply 1 all over 12. So sometimes you might see it written like that in textbooks or online. And so there we have it, the variance. And of course, just to finish off and be, complete in our analysis, the standard deviation of x, which is of course the square root of the variance of x, is simply given as the square root of b of our expression we just derived there, which is b minus a plus 1 all squared minus 1 all over 12, and we can close that off there. So there you have it. We have derived an expression for the expectation, which was a plus b over 2, the variance, which was b minus a plus 1 all squared minus 1 over 12, and of course the standard deviation, which is the square root of that. One of the key techniques here, or one of the key elements in us being able to do that, was using the formula for the sum of consecutive squares and also just the sum of consecutive integers. And then, of course, recognizing that you can take a summation from x equals a to b, can rewrite that as the difference of two summations. And of course, there was some quite heavy algebra there where we were trying to sort of push through the denominator in some sense into our numerator so that we were able to factorize. I hope that video was informative, and I hope to see you in the next one.